that's it. Q&A handled. So please, if you have any questions, even after the course, please write your questions there. I will be monitoring it for a while and answering some questions there. But to go into today's materials, today I have 3 lectures and then 1 example large hands-on in the end. And the first lecture will be just, there are no hands-ons there, it's just a lecture given by me. And this is mainly the work I have myself done with task-based parallelism in the context of two-sided matrix algorithms. More specifically, I have written software for solving dense non-symmetric eigenvalue problems, where in several cases I have seen several fold improvements in the performance due to the fact that I converted from a ScalAPACK style code where you have an MPI and the synchronizations happening into a task-based algorithm implemented on top of StarPU that then allowed me to get rid of a lot of this synchronization point in the code and thus improve the overall performance by keeping more and more CPU cores busy. Whereas the ScalAPACK code would have several periods when only subset of the core was active. After that, I have 2 lectures where I basically just go through the very basics of StarPU runtime system. And again, the main point is that the OpenMP, it is more a better standard, but it only supports shared memory and with some features also support GPUs. Whereas StarPU is a research project that is much more powerful. You can do it in shared memory, you can do it in distributed memory, and you can do it with accelerators. The downside is that it is a research project, so it has smaller, less people packing it. So it's developed at the University of India, and that's why you cannot really necessarily expect as much support as OpenMP is getting in the future. But it has more features, and if you're, for example, interested on seeing if you can benefit from task-based parallelism in the case of distributed memory, then StarPU might be a good place to go and see if you could actually benefit from it. But in general, StarPU is not necessarily the place to start because it requires much more initial investment to get the code up and running, whereas with the OpenMP, you can just add a couple of pragmas and see what happens. So there is this presentation I'm giving to you. You can go and download it from my ResearchGate profile. And in the presentation, I'm showing you this slideshow type of thing that shows you basically, I have captured how a matrix gets updated over time when the algorithm is progressing. So I have the slideshow type of thing happening, and that's why the presentation itself looks like it's 100 slides, but most of the slides are gone through very quickly. If you want to see the actual animation, I've also uploaded to YouTube, and the link exists here. So if you get curious, just go and see it. And I will be now swapping to the presentation. Yep, so this is a presentation I gave over a year ago, locally here at the Umeå University. But then when I was thinking how I could tell you something about my own work, I remember this presentation that was pretty much meant for this type of audience. So for people who are not necessarily familiar with the eigenvalue problem solvers, but would like to know how these solvers would benefit from task-based parallelism. So eigenvalue problems basically look something like this. So we have 2 matrices, A and B, and we want to solve an eigenvalues lambda I and the corresponding eigenvectors xi that fulfill this equation shown here. So you multiply the matrix with the eigenvector, and what you get out is just a scaled version of the same eigenvalue problem. You can also have a generalized eigenvalue problem where you have matrices on both sides of the equation. And for my codes, I'm assuming that matrices A and B are dense and non-symmetric. If they're sparse, then there are different kind of softwares and techniques to solve them. And the same goes if the matrices A and B are symmetric, then again, you will end up using a slightly different kind of techniques. But there do exist some task-based implementations for the symmetric case as well. But everything I've done deals with the dense non-symmetric matrices. So our idea is to do the solution in several steps. So we start from a dense matrix. So the entire matrix, or at least most of it, is filled with the numbers. There are no zeros there. And the first step is to take matrix A, and we construct an orthogonal matrix Q1, and we apply it and its transpose from both sides, and we get a second matrix H, which is an upper Hesselbeck matrix, meaning that everything above the second subdiagonal is non-zero, and everything below it is zero. So we will start eliminating some entries from the matrix. And after this step, we will do so-called Schur reduction, where we then go and reduce the matrix into quasi-triangular form, where it means that on the diagonal we have either 1 by 1 or 2 by 2 blocks. And once we have done this, we can then go and investigate this diagonal box and get the eigenvalues of the matrix A. Then there is second type of thing you can do to the matrix once you have computed this so-called Schur form here, which is that you will take a subset of diagonal blocks and then you apply a set of transformations to move these blocks to the upper left corner of the matrix. Then a little bit about the background of the algorithms that I've been using. So the Schur reduction is performed using an algorithm called the double shift QR algorithm, and this is an older algorithm, so it starts by us solving a 2 by 2 eigenvalue problem in the lower right corner of the matrix, from which we will get two shifts, lambda I and alpha lambda 2. Then we will transform the first column of the matrix in the first column of this shifted product matrix shown here. And then this is done with applying two small 3 by 3 Hausdorff reflectors from both sides. So in these algorithms, you will end up updating a subsession of the matrix, and every time you update it from the left, you will see that we are updating a couple of rows in the matrix. And every time we are updating the matrix from the right, we will update a couple of columns in the matrix. And these are all nicely localized. They only affect a part of the matrix. And what happens here is that you will actually end up creating some fill-ups. So at first you have this upper Hesselbeck form here. You will apply the transformation. You will create fill-up here. And once you apply it to the right, you will end up creating more fill-up to the matrix. So you end up forming this 3 by 3 bulge to the below the diagonal. And the next step is that we will remove this bulge by applying a set of Hausdorff reflectors from the left and to the right, and every time we do it, we will end up moving the bulge down one row and one column, and we'll repeat this process until we have managed to push the bulge all the way to the lower right corner of the matrix. And once the bulge is there, we will eliminate the final remaining element here, and we will end up to a matrix that is back in the upper Hesselbeck form. And then we will go investigate these elements here in the subdiagonal entries in the lower right corner of the matrix. And if we conclude that the entries are very tiny, then we will set them to 0, and we end up decoupling this 1 by 1 block here. Or if it turns out to be this second to last subdiagonal entry that is very tiny, then we'll end up deflating or decoupling a 2 by 2 block. And this is the whole idea. We will 1 by 1 do a set of bulge chasing, and then we will start to decouple these blocks until we have managed to decouple all the diagonal blocks from the orthogonal matrix, and thus has successfully computed the eigenvalues of the matrix. In order to improve the performance, something like 20 years ago, this kind of improvement was introduced called multi-shift QR, where instead of solving just 2 by 2 eigenvalue problem at the beginning, we will actually solve an eigenvalue problem that is m times m. So we'll get total of m shifts computed from it, and these shifts are the eigenvalues of this subdiagonal matrix here. And then we can actually generate several bulges on the diagonal that are just placed here right next to each other. In this instance, we get 8 shifts, and from each shift, each pair of shifts we will get 1 bulge, so we have 4 bulges on the diagonal. And then we will do this bulge chasing now in a pipeline manner for all these bulges simultaneously. And there we apply a trick where we restrict these updates to a small diagonal window. And we are making this diagonal window small enough that it can fit in the L2 cache of the CPU. And therefore we can get much higher memory bandwidth out of it and thus improve the performance. Simultaneously, when we are doing this, we are also accumulating all the transformations to an accumulator matrix. And we will then later on use this accumulator matrix to update the rest of the matrix from the left and from the right by doing matrix multiplications here. And we can introduce additional level of parallelism to the code by simply splitting these bulges that we are chasing during this bulge chasing step into several groups, and then just doing all these groups in parallel. So we'll do a bulge chasing here inside the window, and we will do bulge chasing inside the second window, and then we will do these off-diagonal updates using matrix multiplications. But now you can already see that there is some potential problems that arise for when we try to do this in parallel, which is that when we have managed to do the bulge chasing inside these diagonal windows and then up them to do this off-diagonal updates using matrix multiplications, you know that there is going to be this overlap. And when we try to do this overlap in parallel, we must make sure that we are always doing the updates in a consistent order. If we have several of these windows, and in case of some of these overlaps, we do them in wrong order, then we will actually end up computing an incorrect result. And in earlier codes, what is happening here is that you will pretty much end up doing certain number of these diagonal windows active. Usually it is the square root of the number of CPU processors available, cores available. And then you go and broadcast these transformations that happen inside each window to all the processes. And then you will do all the updates from the left, and then you will do all the updates from the right. So when you do the bulge chasing step, you have a concurrency of square root of b. And when you then do the off-diagonal updates, you will end up a degree price on p. So during this step, you could theoretically use all the CPU cores to do the computations. But again, there must be some coordination being applied, and way it's done in practice is that first we do from the left, and once we know that everyone has done the updates from the left, everyone could do updates from the right, and this is way all the algorithms guarantee that things happen in the correct order. So here you can see a hypothetical trace showing what is actually happening on the real time. So on the horizontal axis, you can see the time, and on the vertical axis, this is meant to represent what each CPU core is doing. So in this example, I have a total of 9 CPU cores. So you can see that we have this bulge chasing that is happening in the diagonal. In this case, we have 9 CPU cores. Take a square root of that, you will get 3 processors active. Then we will do all the updates from the left. And once those are more or less done, then we will do all the updates from the right. And then we will do, again, the bulge chasing and move the bulges a little bit more forward and repeat this process until all these windows have reached the lower right corner of the matrix, and we can move on to the deflation checks. Then around the same time, these multi-shifts were introduced. There was also a second technique called aggressor deflation introduced that attempts to improve the convergence rate of the algorithm. So this previous bulge chasing, the idea here is to restrict the updates to a smaller section of the matrix, load them to cache, and thus get a better performance. What the AD attempts to do is that it tries to speed up the convergence rate. And what's happening there that when we're computing the shifts for the next bulge chasing step, you will instead create something called AED window. And inside this window, you will take this submatrix that is in upper form, and you do recursive QR for it to get it to real true form. And once you then propagate the transformations outside this window, from the left, you will note that this element here will end up inducing a spike immediately to the left of the AED window. So we are now losing the upper structure, at least momentarily. And once we had done this, we can then go and look what are the elements in the spike. And if it turns out that the element in the spike is very tiny, then we can set it to 0, and we will end up deflating 1 by 1 block here. And if it turns out that that element is very large, then we will do Eigenvalue reordering, and we will apply a set of autocurrent transformations inside this AD window to move this failed candidate to the upper left corner of the matrix, and it will then push the remaining blocks down, and we can then go and evaluate the next block. And in this way, we can systematically evaluate every single diagonal block in this AD window and see if we can set the corresponding element in the spike to 0 and thus converge an eigenvalue. So this is the overall the algorithm looks like. We will start from the upper half of the matrix. We will place AD window here. We'll do a Schur reduction for it, which produces the spike here. And then we will systematically go and evaluate every single diagonal block in the AD window. If it happens to be a tiny element in the spike, we will set it 0 and converge. And if it's large, we will do eigenvalue reordering and repeat the process. At the end, we will end up usually having a situation where we still have some of the spike remaining. We will do a Hesper reduction step, and so we get rid of the spike. We are back to a matrix that is partly in a real Schur form, so this part is already processed, and then the rest of the matrix is still in a Hesper form. And then we will do the bulge chasing step using multiple bulge chasing windows. And after doing that, we'll repeat back and do an XAD. So it's pretty much AD, bulge chasing, AD, bulge chasing, AD, bulge chasing, until we have managed to transform the entire matrix to reach Schur form. So this is how it will again look at a trace. We will end up doing AD here, and then we will do bulge chasing you showed earlier, and then we do AD, aggressive deflation. And here I've actually drawn 2 of them because it can happen that sometimes you will discover that you can actually converge even faster. So you do a second AD after finishing the previous one. And after you conclude that it doesn't make sense to do more ADs, you will end up doing bulge chasing step. And here is even more extreme case. Sometimes you can have something like 4 ADs happening consecutively right after each other. And the thing you can observe here is that even though during the bulge chasing step, for most of the time, we can keep all CPU cores busy. When we do the AEDs, if they are done sequentially, almost all cores are idle. So that we are not using those clock cycles for anything useful, which is, of course, problematic if we try to do things in parallel. Amdahl's law comes in and tells you that you will have you really cannot benefit that much from parallelism after a certain point. So what was introduced in the previous parallel code is that you will do the AD step also in parallel. But due to the fact that the AD step is happening inside such a small window, it doesn't make sense to use all the CPU cores to do it, because in that case, you would just end up actually running slower due to all the extra overhead in the synchronizations and communication. So we usually use the square root of the CPU total number of CPU cores to do the AD. So we will get a little bit scalability here, but it's limited, and still we have quite a lot of CPU cores idle when the AD is occurring, and this is of course bad for the performance. So what could we do with the task-based parallelism? So we will go and take all these operations, things happen in the diagonal, and then we have the updates from the left and updates from the right. We can go and cut them into subtasks to get more parallelism out of it. And then you will end up getting a task graph that looks something like this. And this is something that I showed you during the Monday's lecture. So we have bulge chasing happening on the diagonal, marked here in the red. Then we have the left-hand side updates that are cut into subtasks to get extra parallelism. And then we have these right-hand side updates here that are also cut into subtasks to get extra parallelism. And what you can also conclude here that this is a task graph for only one set of bulges being changed down the diagonal. And I earlier told you that we want extra parallelism, so we actually have multiple windows being chased across the diagonal. And that's why we actually get to several copies of this kind of task graph, and they are all mangled together into this hugely complex task graph. And there are several benefits from this, for example, that we don't actually have to do any synchronization. So remember earlier that we will do all these diagonal windows and then updates from the right, updates from the red. You will end up synchronizing. But if we do this in a task-based manner, then the dependencies between tasks will make sure that the overlapping areas where you end up updating the matrix are done in a correct order. So again, we have the critical path happening for it. And then the tasks that are dependencies for the critical path. And then if you have extra cores, we can go and schedule them earlier until a certain point until we have to advance along the critical path. So this is all things that I mentioned during the Monday. Now I'm just telling you where these task graphs actually are coming from. So the end result is a task graph that looks something like this. And I'm again reminding you that this is a task graph that came in a very tiny problem. So this is the matrix was, if I remember, a couple of hundred variables in it. And it took several minutes to generate this graph here. In a real matrix, in case of real matrices, you will end up in task graphs that can have millions of tasks that are, of course, distributed over a longer time period because these tasks are generated gradually. But still, there is no way for me to show you a task graph that has 1 million tasks. Instead of I'm just showing you this very tiny one. So what other benefits of task-based processing there are? Let's have a bit repeat. The first one is a better load balancing because you are not fixing the computations to a specific CPU cores. You are allowing the runtime system to schedule the computations to the available cores dynamically. We can use task priorities to prioritize certain things. Mainly, we probably want to prioritize critical side updates here because they will, in some point in the future, feed back the critical path, whereas the lowest priority can be given to the right-hand side updates because they don't feed back the critical path. There is no information flowing from here to this side. All the information comes to the critical path to the right-hand side updates. Then there is, of course, accelerators. So each task can have multiple implementations and one implementation for a CPU and one implementation for GPU, and the runtime system can then go and attempt to use performance models to decide if the task should run on a CPU or on a GPU. And for distributed memory, it will automatically transfer, and for the GPU as well, it will automatically transfer the data to the correct memory space or across the network. And in case of distributed memory, what happens is that each node will have its own copy of the task graph, and they also know who is supposed to execute a given task. So here I have highlighted the task that the node number 0 is supposed to execute by using by using a darker color here. And then every task also knows where the data is located. So let's say this task here knows that it is going to execute on node number 0. And it knows that it needs the output data from this task before it, and it knows that the data is located in node number 3. So it can do a receive. It is telling that I would like to receive data from node number 3. And node number 3 knows that after executing this task here, that node number 0 is going to need the data. So it is going to do receive, and so on. The task graph, in some sense, gets updated, it gets augmented with these extra tasks that tell it to send or receive data from the other nodes. And all these communications will arise naturally from the task graph itself and the way the data is distributed across the different nodes. And now I come to the second half of my presentation. So what I've done here is that I run my code on a cabinet guys on a single node using 28 CPU cores, and then I would actually capture on real time which part of the matrix gets updated at any given time. So on the left, you can see this matrix that is in the upper Hespec form. And on the right, you can see the Q matrix. So this Q matrix is the matrix that when applied to the matrix A is going to, from both sides, is going to then reduce the matrix to quasi-upper triangular form. So both of these matrices has to be updated in order to during the computations. And the first thing you note here, it is a little bit not necessarily that visible. We have an AED window here. So the algorithm starts with the AED. And you can see a little bit action happening there. It is doing the recursive QR, and then it's doing the deflation checks until it has finished and computed all the shifts. And the next thing what happens here is that you can see the first bulges window appearing in the upper left corner of the matrix. And we are still actually executing some tasks that are related to the AED step because those tasks do not feed back, are not in any way related to the computation of the shifts that are required to generate the bulges here. So there is some overlap that can happen between the AED step and a bulgation step. And now what we see happening here is that the bulgation windows slowly start appearing here. So you can see that we have several windows that are happening concurrently and independently from each other. And then you can see this color green here indicating that we are doing updates for the left. And these were the tasks that fed back to the critical path of the algorithm. And you can see a little bit blue here that are the right-hand side updates that did not feed back to the critical part of the algorithm. So the algorithm is kind of behaving the way as we expected. And then we let this algorithm progress, and you can see that the same pattern repeats. We are having these bulges windows occurring here more or less independent of each other, and in parallel, we are doing the updates from the left that this task fed back to critical path, and you don't see any blue because the way the code behaves is that it will always prioritize the bulges windows and the left-hand side updates, and all the updates that operate from the right are given the lowest priority. And at this point of the execution, these tasks are enough to keep all the CPU cores busy. And you haven't seen anything on the right, and this is because these are all right-hand side updates here, and they are given even lower priority than the right-hand side updates that act on the this left matrix here. So at this point, we actually have an excess of tasks that don't need to be executed yet. And later on, you can see that now there is some blue appearing here. And the reason why these right-hand side updates appear now is that there isn't enough work here remaining to keep all the CPU cores busy. So we still are doing these high priority bulge-chasing tasks here, but when we do the left-hand side updates, we know that there are only a few of them, so some CPU cores start becoming idle, and they are therefore moved on to executing these low priority right-hand side updates here. And they form this kind of wave pattern here. And you can also see it in the task graph I showed you earlier. So this is basically here one bulge-chasing step, this is second bulge-chasing step, and this is a third bulge-chasing step. And you can see a lot of blue here. These are all the low priority right-hand side updates that do not feed back to the critical path. And the way this task graph gets drawn is that it just pushes all the tasks that do not feed back to the earliest steps in the task graph to all the way to the right in the figure. So this is basically the illustration here that most right-hand side updates do not feed back to the critical path. And then finally, we reach a point where we have to the last remaining bulge-chasing windows here still doing something, and then we have this low priority right-hand side updates being executed here. And what happens in the next frame, what happens in the next frame once we have finished the last set of bulges being chased out of the window is that immediately we will move to the next AD step. And we are still executing some of the low priority right-hand side updates from the bulge-chasing step. And this is huge contrast to the earlier code that I showed you, where there was explicit synchronization happening after the bulge-chasing step before you were allowed to move to the AD step. And when you're doing a task-based manner, there is no need to synchronize such a thing because the runtime system makes sure that things happen in a sequentially consistent order. So now we are doing the AD step and using a subset of the CPU cores to do it. And all the cores that don't have nothing to do from the AD step, they are still being kept busy by doing these low priority right-hand side updates. And you can see that once we have finished the AD, we will actually end up doing a second AD in a row. And still, all the cores are busy because if they are not doing stuff for the AD, they are doing bulge-chasing related right-hand side updates here. And we're going, and we will end up reaching a point where we will start the next bulge-chasing step. So this is the first bulge-chasing window from the second bulge-chasing step. This is the recipe reduction that happens after you have done the AD. And you can still see that we actually have some of the low priority right-hand side updates occurring from the previous bulge-chasing step. So what we have done is that we have earlier this bulge-chasing step here separated from the ADs, and then bulge-chasing step. We have pushed all these things together so that we can actually run bulge-chasing AD simultaneously. And we have gone beyond that so that we are actually now doing two bulge-chasing steps that were previously separated by at least two global synchronization points, and we are allowing them to happen at the same time. So we now have one AD finished there, and we have two bulge-chasing steps happening simultaneously. And again, the bulges are being chased here down the diagonal. And you can see that again, we have the same pattern that we have this high priority pulsation windows here, and then some of these left-hand side updates that did feedback to the critical path. Then we are doing some right-hand side updates from the second pulsation step, and we are still doing some right-hand side updates from the first pulsation step. So these are really, everything is overlapping. And in some point in history, we will end up reaching a point where we will end up starting to do the second series of AEDs here. And now you know that at this point, you actually see some activity on the right-hand side matrix. So what has been now that the task pool is getting depleted, but we still have all the tasks that act on the right-hand side matrix to keep all the cores busy. So now we will end up doing again a sequence of AEDs on the diagonal. We do several of them. And all the time, even though there is nothing to do on the left-hand side matrix, all the otherwise idle cores can work on the right-hand side matrix until we would then reach on the next pulsation step. And our result end up being that when we compare this code against the previous state-of-the-art code that is written in MPI, we note that we are more than 2 times faster, depending on what is the actual size of the matrix. And if you go to a different algorithm that is not iterative, in case of the QR, the iterative nature causes that occasionally there just isn't that much parallelism available, regardless how you implement it. But if you look at the Eigenvalue reordering step, that is a direct method, there is no iterative involved. There we actually get a much higher speed up that is between 3 and 5 times faster than what could be done with the MPI. And all this speed up is coming from the fact that we are removing all the global synchronization points and instead allowing the runtime system to make sure that all the data dependencies are being respected. When it goes to scalability, in this figure, you can see on the horizontal axis, we have different matrix sizes all the way to 20,000 to 160,000. And then we have runtime, and then we have different number of nodes. You know that we will get the really good scalability all the way up to 25 cores as long as the matrix is reasonably large. And when we look at the Eigenvalue reordering step, you can see even better scalability. So in case of Eigenvalue reordering, we pretty much see almost linear scalability all the way to 25 nodes. And each node has a 28 CPU core seat. So it's 700 cores. If we look how much idle time we end up having, this is in a shared memory for Eigenvalue reordering. And you can see, again, different matrix sizes here, and then what fraction of the execution time goes to actually doing useful work in this teal color, how much goes to idle time and how much we have overhead. And you know that as long as matrices are reasonably large, there is practically no idle time or overhead occurring. It is, and if you would go and look how the MPI code runs, you will end up running much slower because the cores become idle when they are waiting behind the barrier to allow the computations to continue. And pretty much all my code is what I've written there is available in a library called StarNEig. It is open source, and it aims to provide a complete task-based software stack for solving dense, non-symmetric Eigenvalue problems. It supports shared memory, distributed memory, and GPUs, and this is all thanks to the StarPU runtime system. And it has much increased parallelism that leads to better performance and better scheduling and load balancing to the task approach. And then it also has overlapping communications and computations. And this is the current status of the library for different steps that can happen when you're trying to solve Eigenvalue problem for standard generalized case in shared memory, distributed memory, and GPUs. This is somewhat outdated. Some of these things that are more experimental are not considered complete, but otherwise this is the current state of the library that I have been working on since 2017, I'm sorry. And this pretty much concludes this first lecture. And I will think that I'm taking a 5-minute break, and then I will continue to the StarPU lecture.